we have a bunch of different limit laws. Things like the limit of a sum is the sum of the limits, the limit of a product is the product of the limits, and even a limit law about composition. What are all of these useful for? On the one hand, they make our lives a lot easier when we're trying to compute limits. We can also apply them to a particular case of functions, polynomials. Polynomials are some of our favorite functions because they show up everywhere and they're particularly useful. Let's combine our limit laws together to see if we can come up with a shortcut for finding the limits of polynomials. Let's see how our limit laws are going to help us calculate the limits of polynomials. First, we know that the limit of the sum is the sum of the limits. That means that when I'm looking at a polynomial that's composed of a bunch of terms, I can evaluate the terms individually. For instance, if I want to know the limit as x goes to some value a of x plus 10, I know that the limit of the sum is the sum of the limits. So this is the same thing as the limit as x goes to a of x plus the limit as x goes to a of 10. Now I know that the limit as x goes to a of just x, this function is x wherever I'm at, so the limit as x goes to a of x is just a. And then the limit as x approaches a of 10, well, this function is just 10 everywhere, so no matter what a is, this should be 10. So look at what I got. I go back here, I want to know the limit as x approaches a of x plus 10, and I got a plus 10. So when I had this x, I could think about just plugging in a as long as this is a polynomial. The second limit law that I have is that the limit of a composition is the same thing as a composition of limits. Now I put an asterisk here because this isn't precisely true, so you should go ahead and read about it in the textbook to make sure that you have the right concept. But for the case of polynomials and the area we want to use it in right now, this is a true statement. This basically means that I look at the limit as x approaches a of the function x to the n. Okay, I think of this as a composition of functions. First, the function that produces the identity function, which is just x on every point, and then the function f of x equals x to the n. Okay, so what I'm looking at here is, essentially, I can bring the limit inside of this exponent. So this is the limit as x approaches a of x to the nth power. Now I know again that the limit as x approaches a of x is just a, so what I end up with is a to the nth power. So no matter what the exponent is here, and I'll have lots of different exponents for polynomials, I can just plug in the value for a instead of x because of this limit law, which again, you really want to read about this in the textbook. There's some special cases that are interesting. Finally, the third limit law that helps me with this situation is that the limit of a product is the product of the limits. This means that if I have a coefficient on the front of my variable, I can separate the two into two separate limits. So for instance, if I have the limit as x approaches a of 6x to the fourth, we just discussed the case of x to the fourth, so really I have the product of 6 and x to the fourth. Since the limit of the product is the product of the limits, this is the limit as x approaches a of 6 times the limit as x approaches a of x to the fourth. Like I just said, we just dealt with x to the nth power, so this is n equals 4, which means what I get here is a to the fourth power, and what I get here, the function is again constant, so this should be 6. Meaning, if I put this back together, 6a to the fourth. Again, comparing with what I did here at the beginning, this means that if I'm looking at this part of the polynomial, this term, with a coefficient and some power of x, I can just plug in the a because of this rule. Putting this all together, the limit of the sum equals the sum of the limits. The the limit of a composition equals the composition of the limits, and the limit of the product equals the product of the limits, means that for any polynomial, which is composed of terms like these, added together, I can just plug in whatever the value I'm looking for the limit into the function. Let's see an example. So for this example, I want to find the limit as x approaches 1 of 6x to the 4th minus 2x cubed minus 16x squared plus 10x minus 1. Because I know that the limit of a sum is the sum of the limits, I can split this all apart. Since I know that the limit of a product is the product of the limits, I can separate each coefficient from the term. And because I know that the limit of a composition is the composition of the limits, I know that for any power of x, I can just plug in the value. Putting all of that together, this is 6 times 1 to the 4th power minus 2 times 1 to the 3rd power, 16 times 1 squared plus 10 times 1 minus 1. So I get 6 minus 2 minus 16 plus 10 minus 1, which all together gives me -3. What we've discovered is that anytime I'm looking at a polynomial and I want to evaluate the limit at any point a, all I have to do is plug in the value of a to the polynomial. This is great. But we have to be really careful with this kind of a law. It only applies to polynomials, or at least we've only shown that it applies to polynomials so far. We also haven't quite made a rigorous proof, but you can believe me in this case. Anytime you have a polynomial, you can plug in the value at which you're trying to find the limit. If you want to challenge yourself, you could try to prove this using more general functions, more general versions of polynomials, and making sure all of your limits are some value a and not some specific number. Good luck, try some exercises, and don't forget that if you have a question, post it in the forum.